Robke here. This is for E, solving exponential equations using logarithms. Talked about this before. If we have an exponential equation, we can rewrite it in terms of logarithms. And by the way, if we have a logarithmic equation, we saw in the last video, we rewrite it in terms of exponentials. So let's do this. Solve for x. Notice it says giving an exact answer. That means I cannot use a calculator for this. If I try to solve this on a calculator, it'll give me a decimal of some kind. But the question is looking for an exact answer. So I think first I should divide by 4. That's going to be 0.03. And now I need to isolate the x. How? By rewriting this in logarithmic form. Negative x is equal to log base 2 of 0.03. So x is just going to be equal to negative log base 2 of 0.03. This is an exact answer. I know it looks weird, but that's exactly what the problem is looking for. All right, so look at this one. See the beautiful quadratic hiding inside. It's not really hiding very well. Hey, that's factorable. All right, it's e to the x minus 3 and e to the x minus 2. Cool. That means that either e to the x is equal to 3 or e to the x is equal to 2. Okay, we've solved both of those. X is equal to ln of 3 or x is equal to ln of 2. Those are awesome answers. I love it. Let's look at one that's a little bit tougher. Now this one at first glance, it doesn't look like it's going to be quadratic, but it actually reminds me of a problem we saw in chapter 1. Because if I multiply every term here by e to the x, I'm going to get e to the x squared plus 1 is equal to 3e to the x. And now it's quadratic, just like the last one. Except this time it's not going to factor, so I'm going to need to use the quadratic formula. Now this may be uncomfortable at first, but remember that this equation is quadratic with regards to e to the x. So when I use my quadratic formula, it's going to be e to the x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And then I need to undo the exponential there, so that means that x is going to be equal to the ln of this crazy thing. And we need to make sure that this is never going to be negative, so we need to think about the square root of 5. Square root of 5 happens to be around 2.24, which means that 3 minus it is still going to be a positive number, so both of those solutions should stay here. If you're interested, that's going to be about 0.962 or negative 0.962. And yes, I'm allowed to have a negative come out. This whole thing can be negative. It's just this part of the inside that can't be negative.
So guys, I'm literally sitting at home editing this video right now. And I was thinking, this is kind of weird, like that these two values were just opposites of each other. That was like very unexpected and isn't usually the case. Certainly if I had solved the problem x squared minus 3x plus 1 equals 0, obviously I would get just these two answers, and they're definitely not opposites of each other. So I thought it was pretty weird that when I introduced the ln into the answer, that happened. So I went and I graphed it, and this is with, I moved the minus 3 to the other side so that I could see that my zeros were there, and there they are. And I was like, wow, like that looks like a parabola, actually. That's like really weird, you know? If I'm mixing, like I've got exponentials, I've got two different exponentials being added together, and one of them's got a negative exponent, the other one's positive. Like I was not expecting something that looked so nice to pop out of here. For comparison, this is the one from the previous problem, and like that's a weird function. That's much more what I expected to see with something combining so many different types of functions together. So anyway, my challenge to you is to prove that this is not a parabola algebraically. It's not, and it's not too difficult to prove that. You absolutely know the mathematics to work that out. Everything you need to know is on this screen, or on this screen, really. So have fun with that.
And that brings us to the change of base formula. This is the fourth logarithmic property that we need to know. It's pretty neat. It shows us that we can actually change a logarithm of any base. In this case, it's base b. We can rewrite that logarithm in terms of any other base that we want. We just need to remember that this number goes up top, and this old base is going to go right here in the bottom. This base is our choice. We could use base 10, base E, base 14 and a half, you know, whatever seems convenient for us. This was super, super important back in the day when calculators weren't as powerful as they are now. You would use this formula to change everything into base 10 all the time, because base 10 was something that people could work with slide rules, the technology of the day. For us, we're going to end up using this only to solve certain things by hand. We don't have calculators to help us out. So let's see some. These are going to be potentially painful. Like this one, nasty looking equation. This is not a secret quadratic at all. How the heck are we going to do this? All right, I'm going to do it a couple different ways just to show you some options. First, this is the method that the textbook recommends. So we are going to take this and we're going to rewrite it. This first term, I'm going to rewrite using the change of base formula. We'll do it in log base 10, but it really doesn't matter. So this is going to be log of x cubed divided by log of 4. And I'm going to do the same thing to the next term. I'm going to use the same base. So that'll be log of x to the 1/2 divided by log of 2. I think at least it makes sense that I should want all 4 of these logarithms to be the same base so that I can eventually put them together in some way. Okay, so now I'm going to use some of my other properties of logarithms. So this will be 3 log x over. Now I want to get these two denominators to be the same. So here's what I'm going to do. We know that 4 is really 2 squared. So I'm going to rewrite my denominator then as 2 log of 2 by taking that exponent out in front, just like I did with the 3. And then up top, we've got half a log of x over log 2. And then we can see that we can combine these two. If I multiply the right-hand fraction by 2 on the top and on the bottom, then we're going to get 4 log x over 2 log 2 is equal to 8. And we can see that, let's see, the 4 divided by 2 is going to cancel out, so I can move that over. We're going to divide the 8 by 2 then, so we'll have log x over log 2 is equal to 4. And then we're going to move that log 2 over, so we have log x is equal to 4 log of 2, but I can rewrite that as log of 2 to the power of 4, which is 16. And from here, since log of x is equal to log of 16, that means that x must be equal to 16. Wasn't that fun? Okay, so other options for how we can do this. Well, first of all, I said that we could have chosen any base that we wanted to. So from the very beginning, right here, if I wanted to write this as ln of x cubed over ln of 4 plus ln of 1/2 over ln of 2. The whole thing works out the same. We're going to end up with the exact same answer in the very end. The final step would have ended up looking like ln of x is equal to ln of 16, and then we still get x equals 16. So it always kind of mystified me, this change of base. Like, wow, I can really rewrite it in any base I want, and it's always going to work. And yeah, it does. All right, so anyway, so that's how the book does it. I want to show you what I would do, because I don't think my mind would go to that. And in fact, I try to avoid using the change of base if I can. I just don't like it. Personal preference. So I'm starting off by looking at, I'm seeing a 4 here, and I'm seeing a 2 over here. And I'm like, you know what? 4 is just 2 times 2. So there's got to be a way that I can manipulate these to get them to play nicely with each other. So my thought was, if I write log base 4 of x cubed, that's equal to something. I'll call it big A. That means that 4 to the power of a has to equal x cubed. But 4 is 2 squared. So now I have 2 to the 2a is equal to x cubed. And I can then rewrite this in logarithmic form, base 2. Log base 2 of x cubed is equal to 2a. I then divide by 2, and I get a half of log base 2 of x cubed is equal to a. Since a is equal to half of log base 2 of x cubed, and a is equal to log base 4 of x cubed, that means that I can rewrite this original equation as 1/2 log base 2 of x cubed plus log base 2 of x to the 1/2 is equal to 8.
So again, I cannot believe I didn't think of this before, but it just came to me as I was sitting here. When we have log base 4 of x cubed, we can just use the change of base formula on that to be log base 2. And then I know the log base 2 of 4 is just 2, right? So boom, there you go. It's even easier than what I did in the video.
Now I'm going to move my exponents out. So I've got 3/2 log base 2 of x plus 1/2 log base 2 of x is equal to 8. I'm going to add those together. 3/2 and 1/2 makes 2 log base 2 of x is equal to 8. That gives me log base 2 of x is equal to 4. Rewrite this in exponential form. X must be equal to 2 to the power of 4, which is 16. You can decide for yourself which one of these methods you find most appealing. I certainly enjoy this one more than the first one. That being said, there are problems, and I'll show you a particular one that I remember in class where the change of base formula actually is really, really nice. But like I said, I'll save that for when we're together. Okay, final one. This one is absolutely crazy looking, right? So without using any technology, we're going to show that this mess on the left is equal to 175. One thing that we are not allowed to do in this problem, since it says show that, we absolutely cannot cross this equal sign. I am not allowed to rewrite this in log form and try to manipulate log base 2 of 175 is equal to that mess of fractions. I can't do it that way. I could do that if the instruction said, you know, verify that this is equal. But because the instruction is show that, that's not allowed at all. This 175 is just kind of a secret check for me. I'm allowed to check my work at the end. If I can make this look like 175, then I know I've got the right answer. So how the heck do we do it? Well, I'm going to ignore the base of 2 for just a moment, and I'm going to focus on its exponents. It's not obvious what to do from here. My eyes first landed on this 4 and 4, and I thought, well, maybe there's a connection there, but nah, I mean, the 3 and the 8 have nothing to do with each other, so it's not immediately obvious what to do here. Let's try this. Let's try rewriting each of these logarithms, though, since we have 2 of them. Let's just try rewriting each of those with the same bases. And again, it doesn't matter what base we use, but I'll use base 10 here. So this is going to be equal to 4 over log of 4 over log of 5. Plus 3 over log of 8 over log of 7. And then I'm going to rewrite both of those. I don't like dividing by fractions. I would like to combine those denominators. Thankfully, both 4 and 8 are powers of 2. So we got 4 log 5 over 2 log 2 plus 3 log 7 over 3 log 2. We can cancel some things out here, right? Those 3's will go. That's going to go. That's just a 2 now. So we've got one fraction now. It's 2 log 5 plus log 7, all divided by log 2. 2 log 5 is log of 25. And now I'm adding that to log of 7, which means that I can rewrite those as a product. This is going to be the log of 25 times 7, which, guess what that is? That's 175 divided by the log of 2. Okay, so now what? We're going to use the change of base formula again, but this time we're going to do it backwards. So this is actually going to be equal to log base 2 of 175. To recap, we just said that the exponent here is all equal to log base 2 of 175. So we've got 2 to the power of log base 2 of 175. And if we use one of the identities that we saw earlier, we know that that is going to be equal to 175. If you're uncomfortable with those identities, then just think of it like this. This exponent here, it's equal to something. Okay, so on the one hand, rewriting just this part in exponential form, that means that 2 to the power of k is equal to 175. However, taking a larger view of this, we have here 2 to the power of, well, k. And we just decided that 2 to the power of k is equal to 175. So, of course, this thing is equal to 175. Whew. All right. Like I said, that one is a little bit of a mind bender, but hope it made sense. Not super likely to come across something that nasty. It's just a lot of algebra and change of base. I think most IB questions will have maybe like a little bit of change of base or a little bit of change of base with a lot of other stuff. Not likely to see something that's this massive and only on that one top. So we're in section G now, graphs of logarithmic functions. As I've said before, these are just inverses of exponentials. So if you're comfortable graphing exponentials, you should be comfortable graphing logs. Take a moment, take in this table of information, take a peek at these two graphs. We've got one example of exponential decay here on the left, and on the right we have exponential growth. The dotted lines are the exponentials, and the solid lines are the logs. Pause here if you need more time with it. Otherwise, we're going to move on and start graphing some of these. So here in this first one, let's do letter B for starters. So that's our function. We're going to find its inverse. We're going to graph both of them on the same axes, talk about their domain and range, asymptotes, and the intercepts. So for starters, let's work out what the inverse of that function is. So we've got y equals e to the x plus 1 minus 3. We know we're going to switch x and y. And then solve for y again. So I'm going to have x plus 3 over here. I know that's equal to e to the y plus 1. We're taking the ln of both sides. It's ln of x plus 3. Let's just subtract that 1 now. There we go. So that's our inverse function. Remember, we're going to label it as f inverse of x. We're not going to leave it as just y equals. We will lose points if we try to do it that way. So now we have to graph both of these together. And I'm going to do the graph while working out the domain and range, asymptotes, and the intercepts. So for the given function, the exponential, I know that's going to have a horizontal asymptote of y equals -3. That means that my inverse function is going to have a vertical asymptote of x equals -3. My original function is going to have a y-intercept when x is 0. That's going to be at e minus 3. You might not know what e minus 3 is off the top of your head, but it's a number that's going to be negative at least. I know that because since e is about 2.728, so minus 3 means we're going to be negative. As a decimal, it is negative 0.282. And I know that it's going to have an x-intercept of, well, when this y is equal to 0, that means I'm going to have e to the x plus 1 is equal to 3. We're going to take the ln of both sides. X plus 1 is ln of 3. So ln of 3 minus 1 is going to be the x-intercept. That's also tough to know exactly what that is, but I actually didn't work out what that is as a decimal, so I'll just throw that in its exact form. That's fine anyway. I know it's going to be over here because I knew it had to be to the right of the y-axis rather than to the left anyhow, because this equation is clearly in the form of exponential growth, so I'm expecting to see that shape turn up. So anyway, yeah, let's just graph that. I've got 2 points. I'm good to go. The domain is, since it's an exponential, that's going to be all real numbers. The range is going to be y is greater than -3. All right, for my inverse, I'm just going to switch these things around. Since the y-intercept of my function was -0.282, that means that the x-intercept of my inverse is going to be at -0.282. And that also means that my y-intercept should be at ln of 3 minus 1. My domain is going to be x greater than -3, and my range will be all real numbers. And my advice, if you were to try letter C or D, where you start off with a logarithmic function, would be to find its inverse, the exponential, as a first step, and then just work with that one. Graph the exponential. That's easier for most people until they get super comfortable with logarithms. And then use what you know about inverses to switch x and y's to get the logarithmic function in that question. It's really not that big of a deal. Now, as an aside, you may have noticed in this example that these functions appeared to have intersected twice, and I just want to take a moment to speak about what those points might be. First of all, in general, this is going to be something that you'll need technology to work out. In our case, that's not really something that you should feel comfortable doing by hand, so don't worry. A calculator will tell you that there's 2 points there. I'll say that the points of intersection, you should be able to work out that they do need to exist along the line y equals x. So that can be a way to help you with some easier ones to work out where the graphs might intersect, if they intersect at all. And of course, sometimes they're going to intersect twice. Sometimes they're going to intersect only once. Sometimes they might not intersect at all. We'll look at this one together in class, I think. Now, this is one that I find pretty interesting, but I would actually prefer to think of it the other way and ask when is e to the x greater than x squared. Obviously, the answers to these two are just going to be complements of each other. If I get an answer of x is less than some particular value for one of them, the answer for the other will be x is greater than that particular value. So we're answering the same question here. Now, there's no way we're going to be able to do this by hand. I can't factor that to make an easy sign diagram, so we're going to have to go to technology. And from there, it's easy enough. Just find their point of intersection. In this case, it's -0.703. From there onward, clearly the exponential is greater than the parabola. You can see in this image that the parabola is sloping upwards less than the exponential is. And as I go farther up, they just get farther and farther apart. So that's fine, but I don't know, maybe that's particular to x squared. Is x cubed going to grow faster than e to the x? Well, we can graph that too. Certainly seems like it, doesn't it? They intersect right here, and the cubic looks like it's growing more steeply than the exponential, but if I keep going up, they're actually getting closer together again. They intersect a second time somewhere. There it is. So in this case, from 4.54 or so, e to the x is definitely going to be bigger than x cubed. So it's still growing faster. And you might try a bigger exponent. Maybe we try x to the fourth. X to the fourth grows pretty steeply compared to even x cubed. And I'd have to look pretty high up, but they actually do intersect way up there. So an open question for you. Is there an exponent, and I'll call that exponent n, such that as x gets much, much bigger, goes to infinity, that x to the n could be bigger than e to the x? In the 3 examples we just saw, it didn't work for n equals 2, 3, or 4. But is there a value that's large enough so that e to the x will never catch up to it. Now, unfortunately, we're going to require some pretty high-powered calculus to solve this, so you're going to have to wait until next year. But don't worry, I promise it's in my plans to show it to you. So here's one that probably looks a little bit easier than it is. You're told, use technology to sketch this graph. It certainly does look like a very complicated function, though. We have something that looks like a hyperbola minus an exponential whose exponent is actually a quadratic. This is a very exciting function. When we go to the graph, we see, oh, it actually looks kind of dull. Unfortunately, if you were to simply sketch that, something that looks like this, even if you worked out what that value was, which was 0.627, easy to find on the calculator. If you just throw arrows there too, because it looks like it keeps going, that's going to be worth very little. We've actually missed quite a bit of this graph. Because what happens as x keeps going to the left? I mean, what's going on up in this area here? Well, we know from right here that x cannot equal 0, which means that we're going to have an asymptote at x equals 0. So what's happening to the left of the y-axis? Well, if we have a negative value for x, then we're going to have a negative here minus an e to a power is going to have to be a positive number. So that means a negative minus a positive. This whole answer is going to be negative. So as I look to the left of the y-axis, I should have all negative y values for any of those x values. And that's about as exact as we're going to be able to say without using calculus methods. But that's enough for us to go to the calculator and then look in some appropriate places. We go to change the window, we don't need to make the y max any higher, but it would be nice to bring the y min a lot lower. Let's try negative 30. That should work in this case. Now, I know that because I've already done the problem. Sometimes this will take some guess and checking on your part. And now we can see the missing part is sitting right down here. We could work out what the maximum point is to figure out the turning point spot. That would be really nice. Oops, you see what just happened there? I didn't get a maximum because I went too far. Let me do that again. That was actually not even on purpose, but that was a good idea. As I go, you can see here that the calculator is telling me the maximum. Even as I scroll to the right here, the maximum part of my interval right now is like -8, -21. As I move to the right, now the maximum part of my interval is a little bit higher. As I move to the right even farther, now I've got the maximum that I want. But if I keep scrolling to the right, all of a sudden now my region includes what's to the right of the y-axis. So now I have that portion of the graph that's going up towards infinity up here. So now there actually is no maximum. And that's why it won't tell me the maximum that I'm looking for. So these window ranges that you choose are very important. You need to be careful with those. Anyway, that'll be our max right there. So we can throw that into our picture. We should have something that looks vaguely like that. And that's going to be labeled. And that's all the important parts of this graph. So the lesson we learned here is graphing with technology is pretty easy, but you need to learn where to look. Zooming out can be really helpful, but if you just zoom out all willy-nilly, sometimes you could zoom out too far and you might not really be able to see what's happening. If I were just zoom out here, a whole lot, then I can't really see what's happening on this graph anymore. So best to be careful. And as I said, later on we'll have calculus methods that'll help us narrow down even more where we should be looking for interesting things in the graph. But it's not as though you're going to have to be searching, in the thousands or something to find some hidden aspect of the graph. Everything should be either on your main window or not too far off. And finally, from section H, which is further work with growth and decay, I just thought we'd look at one single word problem. Here we have a parachutist jumping from a hot air balloon. Now, we're interested in his velocity over time. So I want you to think about that without even looking at the equation. If we have their velocity compared to their time, how should this be changing? Well, before they jump, they should be at 0, and then their velocity should be increasing over time. But if you know some physics, that increasing is going to slow down to, at some point, what's called terminal velocity. And there's going to be a horizontal asymptote here. Now let's go to the algebra and make sure that makes sense. So we notice that when t is equal to 0, this is going to be 1 minus 2 to the 0, which is 1. That's 0. 0 times 60 is 0. So I was correct that it goes through the origin. And as time gets really, really, really large, our velocity is going to be 6, 1 minus 2. Okay, I'm going to write this in here. That's not technically correct, but for simplicity's sake, I'll write that for right now. That's my very, very large t value. And this is 60 times 1 minus 1 over 2 to the infinity. We've talked about this. This is essentially a 0 here. So we have 60 times 1. So that horizontal asymptote should be at 60. So now I got a pretty sweet looking graph, even though I wasn't even asked to draw one. We really just want to know when is the speed going to reach 50, which I can draw in here. I want to know where that graph is going to intersect with y equals 50. Not easy to do by hand. So as you can see, solving this equation by hand is kind of messy, and we get this awkward answer of log base 2 of 1/6 divided by negative 0.2. Although I suppose I can do a little bit better than that. I can absorb that negative, first of all, as an exponent on the 1/6. So that can give me log base 2 of 6 over 0.2, and then 0.2 is really just 1/5. So since I'm dividing by a fifth, that could be the same as 5 log base 2 of 6. Of course, we could just go to a calculator. We could graph the log function, graph the line y equals 50, and find that point of intersection. And the calculator will tell you that this is about 12.9. So that's it for chapter 4. Congratulations if you made it this far. We've talked about quadratics, some basics of functions, exponentials, and then logarithms. And I know it's been pretty fast, but unfortunately, that's just the nature of this beast that is HL mathematics. Looking ahead in chapter 5, we're going to see how to transform these functions, how to stretch them vertically and horizontally, and how to move them around in the plane in all directions. We'll also talk about the reciprocals of functions and what happens when we take the absolute value of a function, or a function of absolute value. Chapter 6, we'll go back to quadratics, looking at discriminants that are negative. We'll also think more in depth about the roots of polynomials and what ramifications that might have with certain algebraic questions. And then we'll finally put functions away for at least a little bit until we reintroduce trigonometry back into your life. Anyway, I hope this video series has been productive and enjoyable for you so far, and looking forward to chapter 5.